Hello, in this video we're going to go over three convergence tests for series. The first one is the ratio test. So what does the ratio test tell us? It tells us that if you look at a sequence of numbers that all of the terms of the sequence are non-zero, and you look at the ratio of the consecutive terms, so an plus 1 over an in absolute value, if that ratio approaches a number L, and that number L is less than 1, then the sequence converges, in fact, absolutely. And if that number is more than 1, then the series diverges. So if the absolute value of ratio approaches something less than 1, the series converges absolutely, and if it is more than 1, the series diverges. Okay, so how do we in fact prove this? First of all, let's look at kind of like what's the deal with this and what's the intuition behind why that would have to be true. As usual, I'm going to put the idea of the proof on the right, and then we'll write down the proof on the left. So if you look at an plus 1 over an, it approaches L, which means this is like roughly L, and we can make this more rigorous. So what does that mean that the ratio is roughly L? It means if you look at the each of the terms, that's roughly L to the n times some constant. So because every ratio being L, it means it's a geometric sum. Now, if L is less than 1, then of course the series converges. We know the series of sum of L to the n converges if L is less than 1. And if L is more than 1, then the series diverges. Now, why is it that for L equals 1 we don't have a choice? Why is it that for L equals 1 this test is inconclusive? The reason is, well, L is equal to 1, then since this is an approximation, it's not clear what the exact value would be. So because that's an approximation. And in fact, there are examples when L is 1, the ratio test is inconclusive. Okay, so we're going to go over this, and by the way, this will have to be B. So we're going to go over the proof of this one, and we're going to make this one rigorous. Okay, so I would like to show that an plus 1 over an is going to be less than 1 at some point. So we're going to use the fact that since L is less than 1, we can make the sequence an plus 1 over an less than 1. So we want to avoid 1. So if you look at the number 1 and 0, so L is somewhere around here. We know the ratio an plus 1 over an is near L. So we want to avoid 1. So we're going to take an epsilon that keeps it inside like pretty close to L. So we're going to take the epsilon to be half of this length. So let epsilon be 1 minus L over 2 in the definition of limit. Now we are going to write down what this means. So there is some integer n such that for every integer that is at least n, an plus 1 over an minus L is less than epsilon, 1 minus L over 2. So now we get to understand an plus 1 over n. So an plus 1 over n would be less than L plus 1 minus L over 2, which is 1 plus L over 2. Now notice that 1 plus L over 2 is less than 1. So, and that's like the key for us. So we're going to multiply both sides by an. We get an plus 1 is less than or equal to 1 plus L over 2 times absolute value of an. Now, if you repeat this, so if you write down an plus 2, that's also less than or equal to an plus 1 times 1 plus L over 2. I'm just going to write it down the same way that we had here. And then I'm going to use the previous inequality, use this inequality. So that gives me another 1 plus L over 2. So that becomes 1 plus L over 2 squared AN. And just repeat that. So in general, we can get AN plus K is less than or equal to 1 plus L over 2 to the power of K times AN if N is greater than or equal to N. So now we can look at the terms of the sequence. So thus, for example, A N plus K is going to be less than or equal to 1 plus L over 2 to the power of K times AN for all K in N. Okay, so look at the sequence on the right. The sum of 1 plus L over 2 to the power of K AN when K goes from 0 to infinity, this converges since 1 plus L over 2 is between 0 and 1. This is a geometric sum. It's a geometric sum and the common ratio is less than 1 and greater than 0. Therefore, it converges. So now by comparison test, the initial sum, the sum of absolute value of AN plus K converges. K equals 1 to infinity. This converges because I'm comparing these two. This converges, therefore this must also converge. And both of them have non-negative terms. So this is greater than or equal to 0. Okay, but this is just the same thing as the sum of AN, except that the first few terms are ignored. And we have discussed that if you are looking at a series, the series converges if and only if you can just ignore the first few terms. If and only if dropping the first few terms, you get a series that converges. Therefore, the sum of AN converges in absolute value. N equals 0 to infinity. So, if AN plus 1 over AN in absolute value converges to something that less than 1, then the series converges. Okay, so that's good. Now, the second case is the ratio of AN plus 1 over AN is L, and L is more than 1. Then the sum diverges. Okay, so if you look at this case, in that case, by the ratio lemma for sequences, we know that absolute value of AN would be unbounded. So in this case, by the ratio lemma for sequences, absolute value of AN is unbounded. So that was exactly one case of the ratio lemma for sequences. And that means AN doesn't converge to 0, because if a sequence converges, it would have to be bounded. But it is not bounded, therefore it does not converge to 0. So by the test for divergence, sum of AN diverges. Because the terms of the sequence do not approach 0, therefore the series does not converge. That was exactly the test for divergence. Okay, so next we are going to do something quite similar, which is called the root test. So what is the root test and how do we prove that? So the root test tells us that instead of taking the ratio of an plus 1 and an, take the nth root of an, absolute value of an. If that limit is less than 1, then the series is convergent absolutely. And if the nth root of absolute value of an approaches something more than 1, then the series diverges. Okay, so roughly speaking, what we need to do is this. We know this is roughly L to the n, which is roughly L. So that means an is approximately L to the n, and similar idea. Sum of Ln converges if and only if L is more than 1. And here L is greater than or equal to 0. So that's going to be basically the same thing. Well, let's put it this way. If L is less than 1 and greater than or equal to 0, well, it is already greater than or equal to 0. Okay, so so the proof is going to be somewhat similar to the previous one. So we are going to do pretty much the same thing. So okay, so we know that L is less than 1. So by definition of limit for epsilon equals 1 minus L over 2, we get there is some capital N in N such that for every N in N, if N is greater than or equal to N, then the distance between nth root of absolute value of An and L is less than epsilon, which is 1 minus L over 2. And this means nth root of absolute value of An is less than L plus 1 minus L over 2, which is 1 plus L over 2. So that means absolute value of An is less than 1 plus L over 2 to the power of n, and of course that's greater than or equal to 0. And this is for every n greater than or equal to n. So we're going to do something similar. So by an example, the sum of 1 plus L over 2 to the power of n equals n to infinity, converges since 1 plus L over 2 is less than 1 greater than 0. Because L is less than 1, so 1 plus L over 2 is less than 1 plus 1 over 2, which is 1. Okay, so now we can use the comparison test. By the comparison test, sum of absolute value of n equals n to capital N to infinity, converges. And that means sum of absolute value of an converges from 0 to infinity. And that's exactly what we wanted to prove. Okay, so now we're going to do something similar for the other part. Note that we don't have a root lemma for sequences, although you could create one, but we haven't really had a need to do that. So we are going to present the proof. So okay, so now in this case the nth root of absolute value of an converges to something that is more than 1. So we're going to do something similar. So there is by the definition of limit, for epsilon equals, in this case we're going to take L minus 1 over 2. That one is positive. There is some capital N in N such that for every natural number, if n is greater than or equal to n, then the distance between nth root of absolute value of an and L is less than L minus 1 over 2. This means nth root of an in absolute value minus L is greater than 1 minus L over 2. So this quantity is between this number and its negative. So the other side, the greater than negative of that, is the one that I'm going to be using. And this means nth root of absolute value of an is greater than 1 plus L over 2. Raise it to the power of n, you get 1 plus L over 2 to the power of n. Now, this is more than 1 because L is more than 1. So that means absolute value of an is more than 1 for all n greater than or equal to n. But that tells you that an does not converge to 0. Because if an were to converge to 0, at some point it would have to be less than 1. Its absolute value would have to be less than 1. So therefore it doesn't converge to 0. So by the test for divergence, sum of an diverges. Okay, and this is n equals 0 to infinity. So this diverges. Okay. Let's now look at the last theorem for this video. This one is called the limit comparison test. So it is still comparing two series, except that this is in a different way. We compare them in a different way. So here's the statement of the test. It tells you, suppose you have two sequences of positive numbers. So it is important that these sequences have positive terms. Suppose the ratio an over bn approaches a number that is a positive and real. So in other words, it doesn't approach infinity and it doesn't approach 0. So the ratio approaches something that is positive, but it's not infinity. Then sum of an converges if and only if sum of bn converges. Okay, so let's again talk about the idea of why that would have to be true, and then we will write down a proof. I will give you like the main idea of the proof. So an over bn is roughly L. What does that mean? It means an is approximately bn times L. So if you look at an, if an converges, then sum of lbn converges. But then divide by L and you get sum of bn converges. This is where you need L to be non-zero. If sum of bn converges, then sum of lbn converges. Therefore, sum of an converges. That's basically the idea. Okay, so now how do we deal with that? I'm going to give you like the sketch of proof because it's actually quite similar to the previous ones. So a sketch of proof would be, you want to make sure that an over bn avoids 0. So let epsilon be L over 2 in the definition of limit. So what you're going to get is you're going to get an over bn minus L is less than L over 2 at some point, and this gives you an over bn is between 3L over 2 and L over 2. Now use the fact that an and bn are positive, so you get an is less than 3L over 2 bn, L over 2 bn, and then use the comparison test. How? If you know this is convergent, if you know bn is convergent, then this would be convergent. If you know sum of bn is convergent, then this would be convergent. And then comparison test tells you that this must also converge. The sum of an must also converge. If sum of an converges, if sum of an converges, then this would have to converge. Divide by L over 2, then that gives you sum of Bn converges. So that's basically the proof of the limit comparison test. Okay, so next time we'll start a new topic. So we'll talk about sequences of functions. Okay, so that brings me to the end of this video, and I will see you in the next video.